Welcome to this fascinating exploration of how chemical reactions behave completely differently when we shrink them down to droplet and nanoliter scales. This is a revolution happening in chemistry right now. Let's start with a fundamental question. Why would a chemical reaction care about how much volume it occupies? Molecules are molecules, right? Well, not quite. The answer lies in understanding surface area to volume ratios. Imagine you have 1 milliliter of reaction mixture in a flask. Now imagine dividing that same volume into 4,000 droplets, each containing 250 nanoliters. Same total volume, but vastly different behavior. The key concept is surface area to volume ratio. As you make things smaller, this ratio increases dramatically. For a sphere, the ratio scales as 3 divided by radius. Surface area to volume equals 4 pi r squared divided by 4/3 pi r cubed, which simplifies to 3 over r. This inverse relationship with radius is crucial. Let's do a back-of-envelope calculation. A 1 milliliter flask might have a radius of about 6 millimeters. A 1 nanoliter droplet has a radius of about 62 micrometers. That's a factor of about 100 in radius. The ratio of radii is approximately 100. This means the surface area to volume ratio in the droplet is 100 times larger than in the flask. That's a huge difference that affects everything about how the reaction proceeds. The first major consequence is enhanced mixing. In bulk solutions, mixing relies on convection and diffusion over relatively large distances. But in droplets, everything changes. The Einstein-Smoluchowski equation tells us that diffusion timescales with distance squared. This is critical for understanding droplet chemistry. Time approximately equals distance squared divided by the diffusion coefficient d. Let's calculate actual mixing times. For a typical small organic molecule, the diffusion coefficient is about 10 to the minus 9 square meters per second in water. d equals about 10 to the minus 9 square meters per second. For a 1 milliliter flask with 6 millimeter radius, molecules need to diffuse about 6 millimeters or 6 times 10 to the minus 3 meters. Mixing time equals 6 times 10 to the minus 3 meters squared divided by 10 to the minus 9, which gives about 36,000 seconds, or roughly 10 hours for complete mixing by diffusion alone. For a 1 nanoliter droplet with 62 micrometer radius, the diffusion distance is 62 times 10 to the minus 6 meters. Mixing time equals 62 times 10 to the minus 6 meters squared, divided by 10 to the minus 9, giving about 4 seconds. That's a factor of 10,000 faster. Visualize this difference. In bulk, molecules wander slowly through the solution, taking hours to mix. In droplets, mixing happens in seconds because distances are so much shorter. Why does this matter? Many reactions are limited by how quickly reactants can find each other, especially in multi-step syntheses, where you're adding reagents sequentially. In droplets, faster mixing means more uniform concentration gradients. This reduces hotspots where one reagent is in excess, which can minimize unwanted side reactions. The second major consequence is dramatically enhanced heat transfer. Chemical reactions generate or absorb heat, and managing this heat is crucial for controlling selectivity and preventing runaway reactions. Heat transfer from the reaction mixture to the surroundings depends on surface area. Remember our 100-fold increase in surface to volume ratio? That applies to heat transfer too. Let's estimate thermal equilibration times. This depends on thermal diffusivity, which for water is about 1.4 times 10 to the minus 7 square meters per second. Thermal diffusivity alpha equals about 1.4 times 10 to the minus 7 square meters per second. For the bulk 1 milliliter flask with 6 millimeter radius, thermal equilibration time equals 6 times 10 to the minus 3 squared divided by 1.4 times 10 to the minus 7, giving about 260 seconds or roughly 4 minutes. For the 1 nanoliter droplet with 62 micrometer radius, thermal equilibration time equals 62 times 10 to the minus 6 squared divided by 1.4 times 10 to the minus 7, giving about 0.03 seconds or 30 milliseconds. Again, we see a factor of about 10,000. Droplets cool down almost instantaneously compared to bulk solutions. This is incredibly powerful for controlling exothermic reactions. In bulk, heat from an exothermic reaction gets trapped and temperature rises. In droplets, heat rapidly escapes to the surroundings, maintaining stable temperature. Consider organolithium reactions, which are notoriously exothermic and temperature sensitive. In bulk, you often need to cool to minus 78 degrees Celsius with dry ice to control them. In droplets, you might run the same reaction at room temperature because heat dissipates so quickly. Now we come to perhaps the most fascinating aspect. Droplet chemistry can fundamentally change which products you get. Side reaction pathways that dominate in bulk can become suppressed in droplets, and vice versa. Let's ask ourselves, why would reaction pathways change just because we're in a smaller volume? The molecules don't know how big the container is, do they? The answer lies in temperature control and concentration gradients. Many side reactions have different temperature dependencies than the main reaction. Some side reactions are favored at higher temperatures. Consider a simple model where you have a desired reaction, A plus B goes to product P, and an undesired side reaction where A goes to waste product W. A plus B goes to P. With rate constant K1, this is the desired pathway. A goes to W. With rate constant K2, this is the side reaction we want to avoid. If the side reaction rate constant K2 increases faster with temperature than the main reaction rate K1, then temperature control becomes critical. This relates to activation energies. The Arrhenius equation tells us reaction rates depend exponentially on temperature. Rate constant K equals A times e to the minus activation energy over RT, where R is the gas constant and T is temperature. Reactions with higher activation energies are more sensitive to temperature changes. If the side reaction has a higher activation energy than the main reaction, even small temperature increases favor the side reaction. Because droplets maintain isothermal conditions so effectively, they prevent temperature excursions that would favor high activation energy side reactions. This is why selectivity often improves in droplet chemistry. In bulk reactions, both main and side pathways can occur. In droplets, enhanced temperature control and mixing can suppress side pathways, giving cleaner products. There's another phenomenon unique to droplets: evaporation. As droplets sit exposed to air or gas, solvent can evaporate, concentrating the reaction mixture over time. Evaporation rate depends on the vapor pressure of the solvent and, you guessed it, surface area. With their huge surface-to-volume ratios, droplets can lose solvent much faster than bulk solutions. This can be advantageous or problematic depending on your application. For reactions where you want to concentrate products or drive equilibria, evaporation helps. But for reactions requiring specific concentrations, it can be a problem. Modern microfluidic droplet systems take advantage of all these effects. They generate thousands of identical nanoliter droplets, each acting as an isolated chemical reactor. Droplets flow through microchannels surrounded by immiscible oil. They can pass through temperature zones for precise heating and cooling, and reagents can be added by merging droplets. Each droplet essentially becomes an independent experiment. This enables massive parallelization for screening reaction conditions or doing combinatorial chemistry. This is revolutionary for high-throughput screening. You can test thousands of reaction conditions using micrograms of material in minutes, something that would take months with traditional batch chemistry. Let's look at a quantitative example comparing yields between bulk and droplet for a temperature-sensitive reaction. Imagine a palladium-catalyzed coupling reaction. The desired product forms with activation energy of 80 kilojoules per mole. A side product forms via decomposition with activation energy of 100 kilojoules per mole. Activation energy for the main reaction is 80 kilojoules per mole. Activation energy for the side reaction is 100 kilojoules per mole. At 25 degrees Celsius, we can calculate the ratio of rate constants using the Arrhenius equation. The ratio of K side to K main is proportional to e to the minus 20,000 divided by 8.314 times 298. This gives e to the minus 8.06, which is about 0.00031. So at 25 degrees, the side reaction is very slow compared to the main reaction. But now imagine, in a bulk reaction, poor heat dissipation causes the temperature to rise to 35 degrees Celsius, due to the reaction exotherm. At 35 degrees, the ratio becomes about 0.00047. This doesn't sound like much, but it's a 50% increase in the relative rate of the side reaction. In droplets, the excellent heat transfer keeps the temperature at 25 degrees throughout the reaction. This means you maintain the favorable rate ratio and get higher selectivity. In practice, this kind of temperature control can increase product yields from 85% to 95% or higher. That's a significant improvement, especially for expensive starting materials. For those interested in the deeper physics, there's a dimensionless number called the Peclet number that characterizes the relative importance of convective transport versus diffusive transport in droplets. The Peclet number equals velocity times length scale divided by diffusion coefficient. When the Peclet number is low, diffusion dominates, and you get very fast mixing. This is typical in small droplets where diffusion distances are tiny. When the Peclet number is high, convective flow dominates. But mixing can actually be slower because you're relying on chaotic advection rather than molecular diffusion. Of course, droplet chemistry isn't without challenges. Let's discuss some practical issues. Challenge 1. Achieving reproducible droplet sizes and compositions requires very precise control of flow rates, pressures, and surfactants in microfluidic systems. Challenge 2. Analyzing what's happening inside individual nanoliter droplets is technically challenging. You need specialized spectroscopic or mass spectrometry techniques. Challenge 3. While droplet chemistry is great for screening and optimization, scaling up to production quantities requires either massive parallelization or transitioning back to continuous flow or batch systems. Challenge 4. Not all chemistries work well in droplet format. Reactions involving gases, highly viscous mixtures, or precipitates can be problematic. Despite these challenges, droplet chemistry is enabling exciting new applications across multiple fields. In drug discovery, researchers can screen millions of compounds and conditions rapidly using droplet arrays, accelerating the identification of lead molecules. In protein engineering, droplets enable directed evolution experiments where individual bacteria or cells are encapsulated and evolved in isolation. In materials synthesis, the precise temperature and concentration control in droplets allows formation of uniform nanoparticles with narrow size distributions. In single-cell analysis, droplets can encapsulate individual cells, allowing researchers to study cell-to-cell variation in metabolism and gene expression. Let me summarize the key concepts we've covered about droplet and nanoliter chemistry. First, surface-to-volume ratio increases inversely with size. Scaling is 3 over radius. This is the fundamental driver of all the effects we've discussed. Second, mixing times are dramatically faster in droplets, up to 10,000 times faster than bulk, due to shorter diffusion distances. Third, heat transfer is similarly enhanced, allowing nearly instantaneous thermal equilibration and excellent temperature control. Fourth, this temperature control can fundamentally alter reaction selectivity by suppressing side reactions with high activation energies. Fifth, droplet-based systems enable massive parallelization, allowing thousands of experiments to run simultaneously in tiny volumes. Finally, applications span from pharmaceutical development to materials science, protein engineering to single-cell biology. Looking forward, droplet chemistry represents a paradigm shift in how we think about chemical reactions. By controlling the physical environment at microscale, we can access reaction conditions and selectivities impossible in traditional glassware. The future likely involves integration with artificial intelligence and robotics for fully automated reaction optimization and discovery, where droplet reactors generate data and machine learning algorithms design the next experiments. This is chemistry reimagined for the 21st century, precise, efficient, and scalable in ways previous generations of chemists could only dream about. Thank you for exploring this fascinating topic with me today.